So today we're going to cover section 4. Today we're going to cover inscribed angles and polygons. So the first is the definition of an inscribed angle and an intercepted arc. So an inscribed angle is an angle whose vertex is on the circle and whose sides contain chords of the circle. So the blue is an inscribed angle. Notice this vertex here is sitting on the side of the circle. The intercepted arc is the arc that's created from the endpoints of either a ray, a line, or a segment. Now, before, I guess in the first chapter or at the beginning of the chapter, we talked about central angles. So the difference between an inscribed angle and a central angle is a central angle, its vertex is at the center. And remember when we covered this, if this angle here was 30 degrees, then remember its arc measure was also 30 degrees. So the central angle and the intercepted arc of a central angle are always the same. On the next slide, we're going to learn that the inscribed angle is going to be half of the arc measure. We're going to see that on the next slide. So know the difference between a central angle and an inscribed angle. Central has its vertex at the center. Inscribed, the vertex sits on the side of the circle. So here is the theorem that tells us how to figure out how big the angle is or how big the arc measure is. So the angle measure is always going to be half as big as the arc. So let's say I told you in this picture arc AC, let's say it is 60. So then I know that this inscribed angle is going to be half of that, and it would be 30. If that vertex was at the center, it would be the same. But when it's inscribed, the angle measure will always be half of the arc measure. So this is the measure of an inscribed angle theorem. Next, we have theorem 1011. Again, the number's not important. This is the inscribed angles of a circle theorem. And this one states that if two inscribed angles of a circle intercept the same arc, then the angles are congruent. So what I'm going to do is I'm going to trace over the two chords that make up angle 1. So angle 1 is created by that chord and this one. Notice its intercepted arc is arc AB here. Then if I trace over and show the chords that form angle 2, notice its intercepted arc is the same. So when both angles, both inscribed angles have the same arc, then those angles are congruent. So for example, let's say I told you angle 1 was 20. You know you could figure out its intercepted arc by doubling it. And because angle 2 has the same intercepted arc, it would also be 20. So if they share the same intercepted arc, the two angles are congruent. Next, more definitions. An inscribed polygon is a polygon with all of its vertices on a circle. Sort of think of this as being inside. So it's a polygon that's inside the circle, inscribed. When we talk about a circumscribed circle, it's going to be a circle that contains the vertices of an inscribed polygon. So here, the triangle is an inscribed triangle because it's inside the circle. This is an inscribed quadrilateral because it's inside the circle, with all of its vertices on the circle. Same with the triangle. All the vertices sit on the circle. So, or you could say that the circle is circumscribed about the triangle. So that's how you could use the word circumscribed. So you could say the circle is circumscribed about the triangle. Or instead of triangle, you could say quadrilateral. So more vocab. We have Theorem 10.12. Again, the number's not important, but the name is. This is an inscribed right triangle theorem. And what this one states, that is if a right triangle is inscribed in a circle, then the hypotenuse is a diameter of the circle. Conversely, you can also state if one side of an inscribed triangle is a diameter of the circle, then the triangle is a right triangle. And the angle opposite the diameter is the right angle. So here we can see that the measure of angle ABC is 90 degrees if and only if AC is the diameter. We can also say this backwards. We could say if AC is the diameter, then the measure, if and only if, the measure of angle ABC is 90 degrees. So you can say it backwards and forwards. Now you can also just, look at this in a common sense point of view. If you realize that this is the diameter, and you know that a diameter, that is going to form a semicircle arc, and you know that that has a measure of 180 degrees, and we just learned about the inscribed angle. When you have an inscribed angle, we know that that's going to be half of the measure of the arc. So we would know that 180 divided by 2 is 90 degrees, making angle B a right angle. So again, there's multiple ways to go about looking at these things. Next, another theorem. This is going to be the inscribed quadrilateral theorem. And what this one states is a quadrilateral can be inscribed in a circle if and only if its opposite angles are supplementary. So they would show that angle 1 plus angle 3, these opposite guys, when you add them, they have to be 180. Same thing here. When you add angle 2 to angle 4, they need to be supplements. That's how you can tell if this quadrilateral could be inscribed in a circle. Obviously, you could inscribe a square because opposite angles are 90 degrees on all four, and opposite angles would be supplementary. Be good here. Useful fact number 1, and this is sort of just rephrasing what we've already seen. An angle inscribed in a semicircle is a right angle. So angle 1 would be a right angle. Again, this is the diameter. It's going through the center. This would be the semicircle arc. Semicircle arc measures 180. Half of that is 90. So again, things we've already seen, just phrased differently. Now we're going to do some examples applying everything that we just covered and more, and even probably some prior stuff. So let's go ahead and take a look at example 1A. Now this is circle O. This is our diameter, or not our center. Now, sometimes it's asking us to find the values of variables x and y. Sometimes you can't do them in order. Sometimes figure it out like a puzzle. Maybe you might have to find y before you can find x. Sometimes you can find it in order. All right, so let's go ahead and see if we can find x first. Let me go ahead and trace over the chords that form that angle that measures 20 degrees. So if I show which two chords form it, you can then now find its intercepted arc, which is what they're asking us to find. X is referring to the intercepted arc of that angle 20. We just learned a theorem, and that was the measure of the inscribed angle. And remember, the measurement of the arc is always 2 times that angle measure. So this arc measure would be 40. Now, in order to find angle y, and angle y is pointing to this whole amount here. So let's go ahead and retrace these chords that are forming this inscribed angle. Notice its intercepted arc goes from here over to here. Luckily, I found x first. So now to find the measure of its intercepted arc, I'm going to add 40 plus 110, use my arc addition postulate, add them, I get 150. And now to find the measure of angle y, remember it's half of the arc measure. So take 150, divide it by 2, and y equals 75. Now let's go ahead and see what we can do in part B. So again, let's trace over some things so we can see where the intercepted arcs are and the different things that we have going on in this picture. So if I retrace the chords that form angle 20, if the measure of that inscribed angle is 20, I know the measure of its intercepted arc will be double that, and it'll be 40. Now, I know it didn't directly ask for that piece, but in order to find x, I needed to find that intercepted arc because I can use the theorem that says when you have two angles that share the same intercepted arc, those angles are congruent. So x is going to be 20 degrees. It's going to be half of that same intercepted arc. And y, this one, and we've seen this one phrased several different ways. Notice this triangle is inscribed in a semicircle. Or we also saw that when one of the sides of a triangle that's inscribed in a semicircle, when its side is the diameter, then we know the angle opposite is a right angle. You could also have looked at this as being a semicircle. If this is the diameter, then the endpoints here form the semicircle arc, and then the inscribed angle that would be opposite would be this y. So y is 90 degrees. So you could either have used the inscribed right triangle theorem to find this. You could have used the fact that it was a semicircle arc, multiple different ways here. Pretty good on examples A and B. All right, let's go on. Let's find how to do C. C as well, I can do this multiple different ways. So this is circle O, and I can find the measurement of the different things. They want us, X is the arc here, and Y is for this arc over here. So the first thing I can find is X, because its inscribed angle is the 60 degrees. So the intercepted arc would be x, and that would be 120. Now, if you know that the total degrees in a circle is 360, to find the green piece, all I really need to do is add 140 plus 120, subtract that from 360, and I get 100. So y is 100. Now, another way that you could have also done this is realize that this is a triangle that is inscribed in the circle. I could also have found the different angle measures. So if this is the angle that has the 140 degree intercepted arc, then I know that this angle is 70. I could have also added 70 plus 60, subtracted that from 180, and found out that this missing angle is 50, and then its intercepted arc would be the y. So that's another way that you could have done it, by finding all three angles of the triangle and then found each arc measure individually. So again, multiple different ways to go about solving these. Let's try example D. So for here, I'm going to first find x. So if I trace over the angle that's forming, the two chords that form angle x, I can see its intercepted arc is the 80 degrees. And I know that x will be half of that, so x equals 40 degrees. Next, I can find y, and I can do this, again, several different ways. What I could do here is, if I realize that this is, again, a diameter, and this is a semicircle arc, I could do 180 minus 80, and this piece is 100. And I know if I have congruent chords, then I also know that I have congruent intercepted arcs. So then this arc would be 100, making this inscribed angle half of that, and it would be 50. So the congruent corresponding chords theorem. We could also have used the inscribed right triangle theorem, again, to find the 180. So multiple different ways here of going about doing these. Yes?
What theorem is the one that makes them both 100?
It's called the congruent corresponding chords theorem. The last example is a proof. Now, I do not know yet if we are going to put a proof on the test, but this chapter does have proofs in it. So let's go ahead and see if we can figure out how to do the proof for the circles. So actually, they start out by giving us circles, but they want us to come up with a proof to prove the triangle's congruent. So we're going to use one of our triangle shortcuts. Remember, it's side, 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 angle, side, angle, angle, side, angle, or hypotenuse leg. So let's see what we got here. So they're giving us that circle O and circle P are congruent circles. So I'm going to go ahead and make my statement and column, all that stuff first. So statements, reasons, I'm going to state my given. So I could say circle O equals circle P, and arc AC equals arc AB, given. So my next statement, and I can go about finding different sides in here that are congruent, I guess multiple different ways. I could actually prove this with hypotenuse leg. I'm going to show you angle, angle, side, but there's more than one way to do this. So because I just showed that these two arcs are congruent, I could also state that their chords are congruent. So AB congruent to AC. And again, that's the congruent corresponding chords theorem. Next, what I'm going to bring in is my measurement of an inscribed angle theorem. And I'm going to state that angle CEA is equal to half the measure of arc AC. And also BDA is half AB. And this was the measure of an inscribed angle theorem. Now, because I was told at the beginning that arc AC equaled AB, I'm going to do a substitution. And I'm going to go ahead and plug in AB for AC. So I'm going to say that angle CEA is equal to half of AB. And my reason is substitution. Now, because both of these angles equal the same thing, I could say that angle CEA is congruent to angle BDA. Substitution again. So far, I have that side marked as congruent. I now have this angle marked as congruent. I need to find one more piece that I could show is congruent. So next what I could do is I could state that angle B equals 90 and angle C equals 90. And this reason is an inscribed right triangle theorem. So if you have a triangle that is inscribed in a semicircle, then we know that it's a right angle, that the angle opposite the diameter is a right angle. Now I can show substitution. Angle B equals angle C. And now I have enough pieces to show the two triangles are congruent. And my reason is angle, angle, side. So this is what I was asked to prove, that triangle ABD is congruent to triangle ACE. And that reason, angle, angle, side. I could have also brought in that each radii is congruent, show adding the two radii together makes two congruent pieces. I could have shown hypotenuse leg here as well. Multiple different ways of going back and proving these two triangles are congruent. This is just one way. So that is it for the notes on 10.4. I don't think I gave you any proofs for homework. Again, I will let you know next week if we decide to include a proof. If we do, I'll give you some for review so you can start practicing proofs again. I know it's been a while since we did some.